Hello, my name is Todd Rothman, and I want to welcome you back to Organic Chemistry 1. In this video, we're going to learn about metals' influence on acidity. Now, before we talked about metals in the earlier part of this chapter, and we discussed how metals are counter ions. What they do is they stay or bond or not really a covalent bond, but an ionic bond. They coordinate with nonmetals that are negative. That's one role that a metal has. And we've discussed that role very carefully, right? So for example, we've talked about sodium hydroxide, right? And I said if we have a sodium hydroxide, that we really need to think of this as Na positive and OH is minus. Because most of the time, the metal is not really important to us because we focus in on the non-metal, the negative charge. So it's important to know what's negative in an organic compound. And so, for example, if I have, let's say, a carbon system, and over here there's a zinc, or actually let's write lithium. So let's say there's a lithium over here. Then I would know the carbon holding lithium, this carbon in blue, is negative. And it's so important that you know that. So sometimes these metals get in your way because they're really just countering a negative charge. Now, this video is not about that. This video is when a metal is next to an uncharged, a neutral nonmetal. And we're going to see how it influences the acidity of that nonmetal. Okay, so that's what we're going to do here. So recognize there's a difference between what we're going to do in this video compared to when we talk about metals being counter ions, where they're just not really involved in any of the reactions we discuss. But in this case, this is very important. This is different than that. Let's take a look. So I'm going to use water as an example, but we could use any neutral nonmetal that would coordinate with the metal and see its properties to be similar. Okay? So here's what we're looking at. If we have water by itself, the pKa of water is around 16. So it's not an acid at all, right? It's not a very strong acid. It's a very weak acid. Okay? Now, what if I put a hydrogen on that water and I made it H3O plus? Well, in that case, when you get to H3O plus, this is a very powerful acid, negative number. Anything lower than 0 is a very strong acid. So water is not strong, but its conjugate acid is very strong, right? Now, what about something in between? What if you want to make water acidic, but not as acidic as negative 1.7? Well, that's where this metal comes in. Now, when we have divalent metals, that means that a metal has 2 electrons in its valence shell, and it's a +2, its oxidation is 2. Well, a metal, like zinc in this case, can coordinate with oxygen. So imagine we have water, and all we really need to do this is have a lone pair. Notice water is neutral, so it's not countering a negative nonmetal. In this case, this zinc is coming next to a neutral water. Well, as the zinc comes closer to the water, the electron pair from water starts to move its direction towards zinc. There's no covalent bond here. This is an ionic characteristic, but the zinc starts to lure the electrons away from water. Now, a +2 will do that better than a +1. So our group 1 metals don't really do this that very well. Group 2 metals, where they have a +2, they have 2 electrons in their outer shell, and they're +2, they're very good at this. They could draw the electrons away from a nonmetal. Now, what does that mean? Well, what that means is that water is not positive, but it's becoming positive. It's partial positive. It starts to lose some of its electron density to zinc. And in turn, because it's becoming partial positive, it can lose a proton quicker. It wants to gain electrons. So either it bumps zinc out, pulls back the electrons from zinc, or it could lose a proton. So what we've essentially done here is we've taken water and made it more acidic. We made it more likely to want to lose a proton. Now, how much more? Well, take a look. zinc water has a pK of 9.6, okay? Whereas water has a pK of 16. Now remember, the pK, that number, is an exponential number. So the difference between these two, if we just did it rough, let's say we round it to 10, so there's a 6 pKa difference. So the difference between these two is 10 to the 6. It's 1 million times more acidic, right? 6 zeros. So we've taken water and made it 1 million times more acidic than by adding zinc to the water. You see that? Now, look, the reality is neither one of these are strong acids, right? Because it's not negative, it's not less than 1, it's not a negative value, but it's much stronger now as an acid than it was without the zinc. And that's the point. So here's a middle ground. We were able to take a neutral molecule and increase its acidity by just having a metal, a divalent metal, coordinate with it. Okay, so that's what we're seeing here. We're going to see a really good example of how this is used in biological systems, this little trick here, okay? But before we do that, let's talk a little bit about other divalent metals. So what other divalent metals can influence the pK of water? So here's our water molecule. And my question is, what metal will make this become more acidic by drawing the electrons of the lone pair? And that's what we're going to see. And so look at the trend here. It turns out that when the metal is small, when our divalent metal is small, it has a larger draw on the electrons from water. Think about it. The smaller the radius around that nucleus, the smaller the radius of the metal, then the stronger its nuclear attraction, its positive attraction to something else, because that something else will be closer to its nucleus. So no surprise, beryllium, which is the smallest in my list of metals here, is going to have the most influence on pKa. Notice that it's 4.3. So beryllium next to water brings down the pKa to 4.3 from 16, right? So that's a very dramatic change in the acidity of water. Okay, now zinc is next up, and then it's 9.6, and we work our way up this list. So we have zinc, and then we have magnesium, manganese, then magnesium, calcium. As you can see here, as you get larger and larger, it becomes weaker and weaker influence on water. And that's what we're seeing. Okay, so this is all group 2 elements and some transition metals that have a positive 2 and has 2 electrons in its valence shell. Okay, that's what we're seeing here in this trend. Now, what I want to do, and this is kind of an optional material. I don't know if you're going to get into this detail from your class, within your textbook or from the professor, but I like to cover this because it's a very powerful idea, and that is the idea that metals can influence acidity for neutral molecules, make them more acidic. The only requirement is that it's going to have a molecule, a non-metal, that has a lone pair, one or more. That's all that's required here. Okay, now I'm going to give you a real-world example of how this works. I'm going to show you something that you definitely do not need to know. You don't need to know this reaction. I just want to give you some insight on how we could use this divalent metal and make it react or make it do something for a reaction that's very effective at increasing the reaction's capability or rate of that reaction. Okay, we're going to see that here. So again, do not memorize this. Okay, and I made that clear here. Do not memorize this. It's just an example. So just take a look at this. You'll appreciate the value. Now, carboxypeptidase A is an enzyme that's in our bodies. And what it does is it breaks apart polypeptides. It breaks peptides apart in our system. So this is part of our digestive system. We release carboxypeptidase A into our environment, and then it grabs onto a peptide and it breaks the peptide apart. That's what it does. Now, what we want to do is figure out how we would do this. So let's say, imagine you and I are trying to figure out how this would work. Okay? Now, here's an important step. This is nowhere near the completion of this reaction. It's just one part of the reaction, the part that we're interested in, okay? The acid-base part. All right. Now, if we look at this right here, what I'm illustrating is that water in red, this water molecule, will bond to the blue.